Anytime you draw two lines extending from a single point in space, you create a flat, two-dimensional plane. Moving beyond that surface and pushing into a third dimension requires a method to generate an entirely new trajectory. In mathematics, we achieve this through a specific type of vector multiplication known as the cross product. Basic operations like the dot product yield a single scalar value. The cross product produces an entirely new independent vector. This new vector is strictly orthogonal, meaning precisely perpendicular, to the original plane formed by the first two vectors. Calculating this exact perpendicular trajectory is a core requirement for navigating, engineering, or computing anything inside a three-dimensional environment. The physical reality of this operation is visible in rotational mechanics. This math defines how physical objects spin, twist, and pivot. Torque is the direct physical application of the cross product, occurring when a force is applied at a specific distance from an axis of rotation. If you put a wrench on a bolt, your radius is the vector running down the handle, and your force is the vector pushing against it. When those two interact, a new axis forms straight up through the center of the bolt. That is your torque vector. Because the wrench and force applied to it sit in one flat plane, the resulting rotation acts along an axis that is mathematically perpendicular to that plane. To calculate forces like torque, we have to understand the cross product through two separate lenses: visual geometry and matrix algebra. This represents the formal geometric definition of the cross product. The first half calculates the overall magnitude of our new vector by multiplying the absolute lengths of vector A and vector B. That length is scaled by sine theta, based on the angle between the two vectors. The sine function peaks when the angle is exactly 90 degrees. Your cross product yields maximum magnitude when the vectors are perfectly perpendicular. If you close the angle and pull vectors parallel, the sine value drops to 0, erasing the orthogonal vector. Once the overall size is calculated, we look at the final variable in the geometric equation, the n-hat unit vector. While the absolute lengths and the sine value provide the magnitude, the n-hat unit vector dictates the strict orthogonal direction. A perpendicular line shooting out of a flat surface has two possible paths. We need a way to determine if our new vector points up or down. In physics, we determine this orientation using a physical heuristic known as the right-hand rule. You start by pointing the fingers of your right hand in the direction of the first vector, A. As you curl your fingers toward the second vector, B, your extended thumb locks in the correct orthogonal trajectory. The geometric equation and the right-hand rule describe the cross product in physical space, but they both require a measurable angle between the vectors. In complex engineering models or software environments, you are rarely given exact angle measurements. Instead, computational systems define spatial vectors strictly by their Cartesian data, coordinate points along the x, y, and z axes. When vectors snap to a rigid grid, we track them using unit vectors I, j, and k for x, y, and z components. This introduces a mechanical problem. We must calculate a strictly orthogonal vector using only independent data points, without measuring the angle between them. To bypass the need for physical angles, we translate the geometry into an algebraic engine, the matrix determinant. This is the 3x3 matrix determinant structure used to compute a cross product. The top row sets I, j, and k as placeholders for the perpendicular vector's axes. The second row houses the coordinate components of the first input vector, A. The third row stacks components for vector B. The matrix determinant functions as a systematic calculator designed to process these specific coordinates through its grid structure. Expanding this stacked matrix allows us to convert the grid into a linear algebraic equation. This 3x3 grid holds the exact coordinates of our orthogonal vector. Applying a specific pattern of cross-multiplication unlocks them. We find the new vector's x-coordinate, the I component, through systematic expansion. Masking the I column isolates a smaller 2x2 submatrix. The cross-multiplication step involves multiplying AY by BZ and subtracting the product of AZ and BY. To calculate the y-coordinate, the mask shifts to the middle J column, applying the same pattern to the remaining variables. The alternating sign rule dictates that the J calculation block must always be subtracted from the total equation. Finally, we shift the mask to the K column, crossing the X and Y components to find the trajectory along the Z-axis. This process results in the fully expanded algebraic equation shown here. This sequence of subscripts and signs constitutes a repeatable algorithmic pattern of cross-multiplication. We have now explored two methodologies: the spatial intuition of the right-hand rule and the data processing of the determinant. Mapping the algebraic equation back onto a three-dimensional physical space aligns the two systems. The I-block calculation dictates the exact tilt of the vector along the x-axis. As the J and K calculations finalize, they lock the vector into perfect orthogonality without calculating an angle. The matrix determinant equation is the mathematical mechanism for generating the physical geometry dictated by the right-hand rule. This returns us to the mechanics of the wrench and the bolt. By feeding the raw 3D coordinates of the wrench handle and the applied force into the matrix, engineers calculate exact rotational torque. This scales to track orbital mechanics, map electromagnetic fields, and maintain gyroscopic stability. The cross product provides the functional framework for defining perpendicularity in three-dimensional space. Mastering the determinant ensures that no matter how complex the coordinate data becomes, one can always extract the exact perpendicular forces driving the system.